All right, hello everyone. I'm Blythe, and I'm here with
Joe.
And we're up at University of Mount Union this week. So Chris and I have been recording different activities related to electric fields, magnetic fields, charged particles, interacting with those fields. Now I'm here with Joe, and Joe, I heard you are graduating soon. That's super exciting.
Yeah, I only got about a week and a half left, and then it's on to newer and greener pastures.
That sounds good. Where are you going to be after graduation?
I'm actually going to be interning with Brookhaven National Laboratory in the spring, so I'll be doing work there. And then next fall, I'm actually going to be going to graduate school, so exciting.
Cool. Yeah. That's cool.
as you definitely know.
That's really cool, national. Yeah. But all right. So today we're talking about a charge repulsion interaction. So pulsive problem. And here we're talking about two like charges interacting with each other, and the force that's produced between those two charges is given by this force here. So that's the Coulomb force. We have this K value that kind of scales the strength of that, and we have the charge of one particle, the charge of the other, and that's over the separation between the two charges squared. And you also can think about back to, how we also looked at the force produced by an electric field. So you can reconceive this as, each charge produces an electric field that's felt by the other charge. So if you write this out to, this expression equals Q times E, then for each charge, you'd have its charge multiplied by the field produced by the other charge. So let's look at the setup for our demo and problem. So I'll scroll down here. Now, today we're looking at, as I said, these two positive charges, and we're going to be launching this particle towards this one, and we'll call this one the target, and this one the incoming one. For now, we're going to consider this target particle as something that's a charge that's somehow fixed in position. So, as I just said, each charge would feel an electric force, that Coulombic force produced by the other charge, and so they could both, be accelerated. But to make things easier initially, we're just going to keep this fixed, but it still produces its electric field. And this incoming particle will give it some initial velocity. Will come in, feel that repulsion. So, like charges, they'll want to repel each other. And so when the charge comes in, it's going to slow down as it's being repelled by the target and eventually be pushed away. So let's look at the code, open up the code editor, and see how we are actually executing this. All right, so we'll run the code, see what it does initially. I'm going to press it and then duck out of the way. All right, so I have this charge coming in with some initial velocity, and right now it just passes by the other. So we don't have that interaction coded yet. And one other nice thing that's simplifying our problem right now is that our process is in one dimension. So we're keeping both particles at the same vertical direction. You could modify the code so that it's 2D and it comes in at an angle and it's deflected by the charge, but right now we're just looking at a charge coming in and being pushed that way. Or that's what we want to happen eventually. All right, now, why would we want to look at this process? Well, we've learned about Coulombic forces. We kind of want to see what it looks like. Now, this also has an application, which we'll discuss a bit later, to nuclear fusion. So we'll see why nuclear fusion is so hard. So people want to be able to run nuclear fusion processes because it's a potential source of energy. You know, it's the same process that's fueling the center of the sun. We know the sun produces a lot of energy. It would be awesome if we could harness that process for energy ourselves. So fusion, as the name implies, requires particles to get really close to each other so they can collide and form a different set of atomic nuclei, and that releases energy in the process. But if they're like charges, they have to get over that repulsive barrier. So they have to have enough energy to come close enough for other sets of interactions to occur. So we're going to see what properties of the incoming particle can make that process easier. So let's look at the code. And Joe, what do we need to modify first?